Okay, I'm ready. I have prepared first part of experiment. The number one, am I visible? And number 11 is this generator. You know it? It produces signal. 1 second, I'll camera high. Shown in blue line here. With the frequency of 1 kilohertz, it's kind of rectangular signal with a frequency 1 kilohertz. Spectrum of such signal consists of 1 kilohertz line, let's say 100%, 1/3 at 3 kilohertz, and 1/5 at a frequency of 5 kilohertz. It's come from this large generator, and we see it as a blue line. It's approximation, kind of approximation for rectangular signal. This signal next goes here. What's the idea in this box? I can use signal to transfer another signal. What's the idea? Let's say I have S0 being S0 max cosine omega 0. I can use it as a carrier, and I want to transfer from time. If I form a signal as S0 as from time cosine omega 0 time, maybe it's better than this, but 1 minus some m is not time. Where m is a modulation index. Anyway, it's a modulation. I have put the carrier signal, this one, under the law, or it's now subject to the law of transferable signal. In my case, switch is off. Yellow line, I will expand it. Here is the yellow line, carrier. Yellow line, so-called carrier. I can change it to, where it is. Maybe it can be 100 kilohertz. Oh, in opposite direction. For example, here it is. Okay. 100 kilohertz. It's a carrier. I can add. And now I need to switch, and I definitely need to change time scale. You can see it. 100 kilohertz being subject to my signal at 1 kilohertz. You see? It's called amplitude modulation. Such process where now I have 100 kilohertz, which amplitude changes with this signal. It's the way how I can transfer information. Such process is called amplitude modulation, because amplitude of the carrier harmonic signal, in my case at 100 kilohertz, is subject to the information. What kind of information? Rectangles. But I can use it for voice, for sound, for data. This can be anything what I need to transfer. Amplitude modulation. If frequency would be, if this will be omega naught 1 plus, if frequency would be subject of change, it would be frequency modulation. AM, FM. In my case, I use amplitude modulation to transfer. I can amplify it, put to antenna system and broadcast to the air. Now question, spectrum of this. Now I would like to see the red line is spectrum. Look at the red digits. Central line, 100 kilohertz, carrier. Next one, 101, the first harmonic of my signal. 103, 105, in an opposite direction. 99, 97, and this one will be 95. I have my signal as, let's say, rectangles in a frequency space omega, triple omega, fifth omegas. Yes? I have amplifier generator supplying omega 0, and I'm changing the amplification rate. What will be the result? Time and internal field with 100 kilohertz. This one 100 kilohertz or omega 0, and this part omega. Spectrum I got omega 0, omega 0 plus omega s, omega 0 plus triple omega s, plus 5 omega s. Omega 0 minus omega s, omega 0 minus triple omega s, omega 0 minus 5 omega s. I have this spectrum of signal located around the carrier frequency. That's how amplitude modulation works. It's interesting. But I want to show something more complex. I got this demo. It's old. I rescued from the junkyard. I have two elements here. One is generator, similar to one we saw. Its frequency controlled by this capacitor, this lower part. And the upper part, special valve. Previously we saw valve with one control grid. This one has two. It allows to perform some operation. If I have two control grids, each controls the output independently. So if I mix this generator signal with amplitude modulated my signal, I will show something new and interesting. First I need to, 1 second, I'll get power in there. I need to power it up. Come on. This one is ground and this one is power. Now I need not this. Oh, okay, I can use it. Do I have another one? I need more. Oh, this one is. So I'm taking my signal with amplitude modulation, holding here, and here, but 1 second. The maximum difference I have. I'll switch to this filter. And I will need this. I have 100 kilohertz here. 5. No, I will adjust to. Can I have 200 here? First. G means ground. Signal, signal, signal. Okay. Here is my signal. I don't need it. Okay. Here is my signal at a frequency 200 kilohertz. I choose 200. Now let's see what I'm putting here. Number 4. Why should I limit myself? Nyquist frequency. The real frequency now is 1 megahertz. Oh, I'm an idiot. I'm waiting for signal. Without the power. Oh, here is my signal. And now question. Can I section 300 kilohertz. It's good. Can we see it? Oh. Okay. I have signal, I have carrier at 300 kilohertz. I will switch camera. I decided to 300 kilohertz is okay. Where are you? Here it is. Signal from the large generator and yellow one. It's a sine subjected to the law of my transferable signal. Now, one moment, I'll get spectrum. I have its spectrum. Central frequency 298, 99 plus 3 plus 5 minus 3 minus 5. Okay. Spectrum around 300 of kilohertz. And what I'm doing now, I'm setting, 1 second. So, at this point, I have around 300 kilohertz. Now, I'll use to mix it with a heterodyne. 1 second. Amplitude. It's not a good idea. I will destroy my scope. Need a divider. Here is the output signal, but what kind of signal gives me heterodyne? Yes, this one is okay. Oh, here it is. It's not ideal sign. It's harmonic, but okay, distorted. With the frequency, take a look. 700 kilohertz. See? 7. $770, something like this. Should be. It's approximate, okay, it's approximately 800. I have this approximately 800. Summed with my signal with a spectrum around 300 and put through the filter with the frequency around, it's 460 kilohertz, central frequency. And what do we see? Looks like it's amplitude modulated signal, yes? But at frequency. I need to. It's not very stable. 1 second, I will make it. Uh, 460 kilohertz. It's a difference between them. I have 300, 800, 8 minus 3. And what about spectrum? 1 second, I'll bring spectrum to the screen. It's somewhere around, right? I got you. Here's our spectrum, and we got central line 469, 470, 472, and so on. Whole spectrum of amplitude modulated signal is transferred at a high frequency. I can use another trick. I will set filter. I'll set this filter. I have ability to use 112. Oh, I can use this one. 800. Kilohertz, and frequency of this one it's a heterodyne signal. What I got here? Here is my spectrum. I have now filtered at 800 kilohertz, but where is now my spectrum? I'm not bad news. Bad news, bad news. Oh, yes. I got my spectrum now at not exactly 800. Filter isn't in very good condition, but at 760. I have transferred from 300 kilohertz to 700. With heterodyne set to 1, it's a bit below 1 megahertz. I can use, for example, I have preset for 100 kilohertz. But I'll need a bit different. I'll set 1 megahertz here. Section 4, 1 megahertz, and let's see. let's say this one. Signal. Okay. Are you signal or what? Here is my signal. One moment, I will synchronize with it. Here is my signal, 1 megahertz. My source signal is at 1 megahertz frequency. I have set field to 110 kilohertz. And let's take a look with spectrum of my signal now. Best filter on those. But idea is clear. Here is spectrum of transferred signal. 1.6 megahertz. Now frequency is above 1 megahertz. I can find the same at a frequency below. Now heterodyne frequency is 900 and I still have the same mirror, so-called mirror channel, 1.7. I have transferred all spectrum to the 1.7 kilohertz from 1 megahertz frequency. Carrier 1 megahertz, it is modulated with 1 kilohertz, and with the heterodyne frequency of 900 kilohertz, it's being transferred to the approximately 106 kilohertz frequency. No, exactly 100. Here it should be 112. It's not an ideal condition. Best one is, best filter is for 475. Can I get it? Traditional for radio broadcasting. Frequency, so-called interim frequency of processing at 465. Oh, here is my spectrum. And where is my cursor? central frequency be different, should be 465, and I see 470, something like this. 400 should be 71, 73, and this small definitely 75. And on the opposite direction, 68, 67, and -5, 64. I have clear spectrum of big generator signal, but transferred to 470 kilohertz. With the process of heterodyne, I can transfer signal spectrum without distortion to virtually any frequency. Idea of signal, of two signal mutual effects. Combine two signal with a frequency difference, you need to transfer two. And with the help of filter, cut off from the resulting spectrum, or at some or at difference. I have 1 megahertz carrier, 100 watt heterodyne, difference 400 approximately. I cut it with the filter for 465, and I get my spectrum at 460. In our case, omega 0 minus omega heterodyne minus omega 0. It's our case. Combining signal spectrum with an additional generator called heterodyne and then cut off or sum or difference at some frequency or difference, you can transfer signal spectrum to any frequency you need. One kilohertz, let's say broadcasted at 1 megahertz, with the help of heterodyne, transferred to 400 kilohertz. Here, with 400, we can apply good selective filter and result demodulate to get information back. Where is my demodulate circuit? Very simple detector, diode and condenser.
Peak detector? Is it a peak detector?
It can work as a peak detector if condenser is quite large. But in our case, it will extract the borderline from the total signal. 0.1 microfarad. Come on. Here it is after detection. Not ideal, but at a frequency 1 kilohertz. My detector is not ideal, but should be better take absolute value and then pass it through low pass filter to cut high frequency components. At the first approach, here it is. Signal demodulated. Not ideal, but something. Sound of the old way of sound. Modulated broadcast received, converted, filtered, demodulated, amplified, and you can hear grandma's sound. Okay. The complex life of signal. It's enough for today. If we have time, we can use this military receiver. I have attached terminals inside, so we can see real broadcasting signals. They are not so nice, but it works. In any way.